And then the floor is open for any questions you may have related to the content of Module 1, Module 2, which is the information you will see on the midterm exam. Okay, you may unmute and speak, or you may type it into the chat. I'm not seeing anything in the chat. Okay, do you have questions related to mini project 2, which is due by Monday, the 10th? Okay, if not, then we're going to move on into the lessons for tonight. We're going to talk about hypothesis testing, parametric versus non-parametric test, and normality. I hope that we're able to get through all of that. If not, we'll pick up with whatever remains next week, but that is what is on the agenda for tonight. To help facilitate our discussion of hypothesis testing, I posted yesterday a set of fill in the blank notes. Hypothesis testing is a topic that is covered in Stat 1401. And it is really an important process and important procedure throughout statistics because it allows us to verify, determine whether our proposed answer to a particular research question is valid, is it on target, is it reasonable, or are we way off base? And so I anticipate that many of you have forgotten that process. So we're going to talk about that process, walk through what that process is, and within that process, we're going to talk about the topic of hypotheses and p-values, and then we will circle back and pick up normality. So this, and quite honestly, we're going to be talking about hypothesis testing throughout the rest of the semester in modules 3 and module 4. This gets us into the area of inferential statistics. Again, one of the uses of statistical research, or even of statistics, is to be able to provide information to support the decisions that are being made. A lot of businesses nowadays talk about making data-driven decisions. And so we are asked to provide information about a variety of population parameters, things like the mean, the median, the standard deviation, the variance. There's a great example that is given in the introduction. It says Georgia's public broadcasting system may want to know how many Georgians watch their programs each week. But again, as we've talked about, it's going to be difficult to survey each and every household in Georgia. So we take a smaller subset known as the sample, and then based on the results from that sample, we then infer or apply that information back to the population parameter. And part of the challenge we have is we have to talk about whether those values, those numbers we have gotten, are statistically significant. Are they different enough from the mean, from the standard deviation, from the variance, depending on what you're testing? Are they different enough to indicate that there's something going on other than simply pure chance? You know, we can get a result based on pure chance, but is the value or values that we have different enough from the mean to say, wait a minute, let's see what's going on? So you'll hear that phrase throughout the lesson tonight and as we move forward. And then again, it's called statistically significant. Is your results, or are your results, different enough from the mean or from the average to imply that there's something other than pure chance going on? And so we use a process called hypothesis testing to verify whether or not our proposed answer to a research question is valid, reasonable, or on target. You can think about hypothesis testing being similar to a court case, because in a court case, you're ultimately trying to decide whether the defendant committed the crime of which he or she is accused. And at least within the United States, we assume that the defendant is innocent until proven guilty. So we start out assuming they're innocent, and then both the prosecutor and the defense provide their evidence that they have collected, and the jury is listening, and then the jury deliberates, and based upon their interpretation of the evidence, they come back and say whether the defendant is guilty or not guilty. Okay, which then is either supports our contention that they were innocent or does not support our contention. So the idea of a hypothesis test is similar to a court case. But again, I want to spend some time tonight walking through the process of hypothesis testing, because I anticipate that many of you have forgotten that process, but since it's been a while since most of you have taken Stat 1401. So again, I have the fill in the blanks notes pulled up here on my computer that I provided to you. Okay, so either hopefully you've printed them off so you can fill them in as we go, or you may have them pulled up on your computer in a Word document where you can type in, the values or the information as we go. So let's get started. Again, a hypothesis, if you think about it from a science perspective, a hypothesis we think about as being an educated guess. Or in our case, it's typically a proposed answer to the research question. And so when we are looking at those proposed answers, there are actually two of them, and that's where we begin. We begin by stating the two opposing hypotheses. Just like in a court case, we have guilty or not guilty. Okay, we're going to have two opposing hypotheses. Okay, again, you can think about it as, right or wrong, left or right, up or down. Again, they're opposing, they are opposites of each other. The first hypothesis is called the null hypothesis. The symbol is the letter H, and it has a subscript of 0. Null is a fancy word from olden days that does imply or mean 0. And so that's why you have that subscript of 0. So the null hypothesis, the symbol is H with a subscript of 0, is a claim, an educated guess, a proposed answer about a population parameter that is assumed to be true throughout the entire hypothesis testing process. It must always contain equal in some form. Now, a couple of side notes. It says a claim about a population parameter. For our purposes, we are only going to be focusing on either the mean or a proportion. There are also hypothesis tests that can be performed on things like standard deviation or variance. Okay, but we don't talk about those in Stat 1401 nor here in Business 3000. Our focus tends to be on the mean, the population mean to be more specific, or the population proportion. And again, that claim is assumed to be true throughout the process, just like we assume a person is innocent of a crime until proven otherwise. Now, it does say that it has to contain equal in some form. And so a lot of questions become, well, what does it mean in some form? Mathematically, that means there are 3 options. Your null hypothesis will either contain the symbol equal, less than or equal, or greater than or equal. Which one you have is going to depend upon the phrasing or the wording in the scenario or scenarios that you'll be given throughout this course in examples, on the quiz, and on the final exam. And so you have to kind of be familiar with what are some words that could imply equal, what are some words that can imply less than or equal, greater than or equal. So hopefully that will not be an issue. I think I may have a short list, not a complete list, but I have a short list that may help you if it's needed. Okay, the second hypothesis is called the alternative hypothesis. Alternative. Its symbol is a capital H for hypothesis with a subscript of A. Okay, A for alternative. I will mention that in some text, okay, in some text, they use H with a subscript of 1. Okay. I use, and I know it's what's used in on your homeworks, quizzes, on your final exam. I use H with a subscript of A. It is a claim about the same population parameter that is the exact opposite of the null hypothesis. They are opposing or opposite of each other. So the null and the alternative are opposites of each other. The alternative hypothesis will never contain equal. The alternative hypothesis will never contain equal. So here again, it's the same population parameter that we use in the null. So again, for our purposes, that's going to be either the mean, population mean, or the population proportion. the mathematical symbols that you could see in the alternative are going to be not equal to, greater than, or less than. And I will point out to you that those particular things are always paired together in that manner. Equal will always pair with not equal. Less than or equal will always pair with greater than. And greater than or equal will always pair with less than, again, because the null and the alternative are opposites of each other. The alternative hypothesis also helps us to determine the type of test. And it's important to know which type of test you have, because this actually affects the calculations of your test statistic that is going to happen a little bit later on. So it's important that you know which type test you have. Now, Minitab is going to do the calculations for us, but again, you need to be familiar with, you have to be able to select the right options when you're using Minitab. So we have what's called a one-tail test. A one-tail test occurs if the if the alternative hypothesis contains either less than or greater than. Now, again, this is the idea here is, are we getting a value that is significantly different from the mean? So again, one example would be if we're thinking about the normal distribution and our mean is the middle, and we're saying, oh, well, my value, I think my value is less. Then at some point, there's like this mark out here where when you reach that point, you are different enough, you are statistically significant. And because you're less than, that region is on the left of the mean, because left is less than. And so it only has one region or one option, the option being that we're less. It could also be, again, thinking about the normal, and it's not the only distribution, but that's the one you can relate to right now. If we were saying it was greater than, again, at some point, we become statistically significant or different enough, but we're greater than, and things that are greater than are to the right. And so again, you only have one option in that you are greater than. Now, I will mention Minitab just refers to it as a one-tail test, which is fine because you only have one option or one region. Okay, but some text, if it's less than, they refer to it specifically as a left tail because the region is on the left. And if it's a greater than, it's often can be referred to as a right tail because the region is on the right, again, because greater than is to the right. So if you see those terms, they're not wrong, but again, your text just simply uses the phrase one tail. The other type test you can have is a two-tail test. A two-tail test occurs if the alternative hypothesis contains not equal. Because the symbol mathematically not equal means it's not the same. So it could be less or it could be more. So if we're thinking about that in terms of a picture, and thinking about being statistically significant, again, relating it to the normal distribution that we're familiar with, we have the mean. So we're just saying it's not equal. So it's not the same as the mean, but it could be less. So I'm going to have a region to the left to allow for the less than option. Or it could be more. So I have that option as well. Okay, so again, in this case, you have two regions, hence the term two-tail. And again, it's important to know which type tail you have, either one tail or two tail, because you're going to have to make that selection when you're doing your bean tab commands and your calculations of your test statistic are affected by which type tail you have. So it's important to know which one you have. Okay, so step 2 is, in reality, we would pose our question, propose our answer, and then we have to go out and collect our sample data and calculate, and go through the processes we've been going through with organizing the data maybe into a table, creating some graphs, calculating our descriptive statistics. That's what you would do in reality, in the real world, if you were doing the research yourself. I don't have time to send you out every time we do a problem to collect data. So for us, you're going to be given that information. So you just have to identify the given summary statistics. I sometimes refer to them as the players. You have to identify the players. What's the information that you need to solve the problem. The summary statistics that you need depend upon which test is being conducted. And we're going to look at a variety of tests. Let me see if I can count for a minute. We're going to do at least 8, probably more, at least 8 different tests between now and the end of the semester. Okay, and so knowing which tests you're going to conduct is going to be important. So you collect your sample data and calculate your descriptive statistics, or in our case, you're going to identify the summary statistics. The summary statistics that you need depends on the test that you are going to conduct. And so really step 3 is going to be to determine which test you need to conduct. And in some cases, it might be that you do that step before step 2. I'm going to focus on tonight, in this fill in the blank notes, 2 of the tests that you hopefully learned in Stat 1401. Now, again, I realize for some of you that's been a while. And then we will, as we go into some that you haven't seen before, such as the 2-mean t-test and the chi-square test for independence and the chi-square test for association, some of those tests that we haven't seen before in Stat 1401, we'll come back and I'll give you the same information. Okay, so 2 that hopefully you're already familiar with or hopefully can recall pretty easily are going to be the 1-mean z test and the 1-mean t test. A 1-mean z test can be used whenever you have quantitative data. and n, which is your sample size, is greater than or equal to 30, meaning you have a large sample. The population standard deviation is known or given, and the one mean z-test is related to the normal distribution that we talked about earlier in Module 2. One of the benefits when you're thinking about using the one mean z-test, for us, the primary thing is, do you know the population standard deviation? We also, if we have a large sample greater than or equal to 30, if we do not know whether the population is normal or not, we can then apply the central limit theorem, because the central limit theorem, remember, forces an unknown distribution to be normal. So if we want or need to conduct a one mean z-test, what information do we need? The things that we need that should be given in the scenario are going to be the population mean, which is represented by the Greek letter mu, and that you'll usually find in your hypothesis. The population standard deviation, which is represented by the Greek letter sigma, should be given in the scenario somewhere. We need the sample mean, which is x bar, which should be given somewhere in the scenario. And we need the sample size, which is n, and that's going to be given in the scenario. And then finally, we need what's called the level of significance, which is represented by the Greek letter alpha. Now, that should be a new term, or maybe an old term that you have forgotten. So I want to scroll down, because I didn't leave room here. I'm going to scroll down to the end of the document and talk about level of significance. Most recently, at the end of Module 2, we talked about confidence intervals. And for each confidence interval, we had a confidence level. That confidence level was the probability that we were correct, or the probability that our mean falls within the stated interval. So in a sense, we were correct because it fell in that interval. We noted that confidence levels are usually stated as percentages, and the most common ones were 90%, 95%, and 99%. Now, they're not the only ones, because we did talk about how that the confidence level could be any value between 0 and 100%. So tonight, I just used a new term called level of significance, or the significance level. And it has a special symbol. We use the Greek letter alpha, but it represents the probability that we're incorrect. What's the chance that my mean does not fall into that particular interval? It's the probability that you come to the wrong conclusion. So confidence level and significance level are related to one another. Confidence level looks at it kind of from a positive perspective, whereas the significance level looks at it from a negative perspective. One other difference is typically your significance level is stated as a decimal rather than a percentage. Together, the two have to equal 1, because if you go back to the idea of probability, if you're going to be probability that you're right plus the probability that you're wrong, that's the two things that could happen, that has to total to 1 or 100%. So if there's a 90% chance that I'm correct, that would imply that there is a 10% chance that I'm wrong, and written as a decimal, that would be 0.10. Again, you take 10, divide it by 100, you get 0.10. 95% confidence level, probability that I'm correct, that leaves a 5% significance level. There's a 5% chance that I'm wrong. 99% confidence, probability I'm correct, there's only a 1% chance that I am incorrect. Okay, which is 0.01. And again, those are the three most popular significance levels. Of those three, 0.05 or 5% is probably the most common that you see, which, if you'll recall, I told you that 95% was the most commonly used confidence level. So that's kind of what we mean by significance level or level of significance, and that will be given in the problem. Now, in some cases, researchers will leave either the confidence level or the level of significance open. They won't state it, so that you as the reader can decide whether you want to base it on a 95% confidence or 99% confidence or whatever, so that you as the researcher can kind of make your own conclusion. Okay, so then the next one, the other one that we talk about in Stat 1401 is a one mean t-test. And again, a one mean t-test is used whenever you're dealing with quantitative data. But now our sample size is less than 30, so we have that small sample. The population standard deviation is not known or given in the problem. And the one mean t-test is related to the student's t-distribution, which again we talked about last week when we talked about the t confidence interval. The statistics that you need for doing a one mean t-test are very similar to the z, with one exception. You still have to have the population mean, which is represented by mu. You're given the sample standard deviation, which is S. The difference, which is the same difference you had with confidence intervals, you use Z when you know the population standard deviation. You use T as in tiger whenever you do not know the population standard deviation. You know the sample standard deviation. You still have to also know the sample size, which is N, and sample size, and you need the sample mean, which is X bar. And you also will be given again your level of significance, which again is represented by the Greek letter alpha. And again, those are two that we study in Stat 1401. We're going to review them in this course. We also talk about one of the chi-square test in Stat 1401. We will actually talk about the chi-square test in Module 4, and there are actually 3 different chi-square tests that we'll talk about. One of them is goodness of fit. Goodness of fit is one of the few statistical analyses that you can conduct on qualitative data. And so we do talk about that in Stat 1401 so that you don't think that qualitative data cannot be analyzed. Chi-square goodness of fit is one of the few statistical analyses that we can do on qualitative data. And again, we will visit that topic in Module 4. We also will talk about analysis of variance, and to be more specific, we conduct what is called one-way analysis of variance, which is abbreviated ANOVA, and it actually is quantitative data that is sorted by a qualitative variable. For example, it might be that we want to look at the weights of shipments, and we're going to sort those shipments by the mode. Were they shipped, by truck, by air, by sea, how they were shipped. So we look at the weights, which is a quantitative value, and we sort it by the qualitative. Maybe we look at blood pressure and we sort it by the type of disease that someone has. Do they have heart disease? Do they have arthritis? Do they have, but you're sorting it by some qualitative variable. That one we'll talk about a little bit later on in Module 3. And then the last one that's listed here is called correlation. Correlation gets us into considering more than one variable at a time. Correlation lets us look at 2 variables, so it's called bivariate, bi meaning 2, so 2 variable, and they're both quantitative. So correlation deals with bivariate quantitative data. And again, we will revisit that topic in Module 4. You will be using app.minitab.com to do these problems. You will not do any calculations by hand. Okay, so you have to calculate and record. That means write it down, the test statistic and its corresponding p-value. Every test statistic has its own unique p-value. Now, again, that's probably another term that you may not be familiar with. So we need to think about for a minute, what is a p-value? A p-value is a probability value. Now, as a side note, if it's a probability value, remember that its value should be between 0 and 1. That goes back to the basic probability rule that all probabilities are between 0 and 1. 0 meaning the event is impossible. No way, no how is it happening. 1 means it's definitely happening no matter what you do, and you can have any fractional or decimal value between 0 and 1. So you'll never have a p-value that is negative, and you should never have a p-value that is over 1. Now, it's a probability value, but what is it the probability of? It is the probability of getting the same test statistic kind of over and over and over if the null, okay, and I'll make a little note out here, if the null hypothesis is really true. Remember, we assume in the beginning that the null hypothesis is true. Just like we assume a person is innocent until proven guilty. The test statistic is ultimately kind of the summary of our evidence. And based on that evidence, then we're going to make a decision about whether our null hypothesis is true or not. But if it's assumed to be true, the p-value is the probability that I get that same test statistic over and over again. Or another way to think about it is that the results from another random sample will be as extreme or more extreme than the results of the given sample. Again, if I go and I collect the data again, what's the chance or the probability that I'm going to get those same results again? Or at least similar results? Or am I going to get more extreme results? Again, because then we're thinking about, is it statistically significant? Okay, don't get so caught up in that little bit of theory. Okay, the important piece is that you know how to use and interpret that p-value, and that's what we're going to do in step 5. Step 5 is we're going to make a decision to reject the null hypothesis or fail to reject the null hypothesis by comparing the p-value and the level of significance. Okay, a couple of things here. Notice that ultimately your decision is with respect to the null hypothesis, because remember, the null hypothesis is the statement that we have assumed to be true. So we've assumed the null hypothesis to be true, just like we assumed the defendant was innocent until proven guilty. So when you get to this stage, and it's important that you note the phrasing here, okay? It is reject the null hypothesis. This would be like saying that the person is guilty. Because to reject the null hypothesis means that the null is false or wrong or invalid, whatever words you want to use. When we reject the null hypothesis, that means that the evidence shows that our assumption that the null is true is wrong. So the null is false or wrong or invalid, which is like saying that a person is guilty, because the assumption was they were innocent, but the evidence showed otherwise, so they are guilty. The other phrase, and it's again important to note this, is fail to reject the null hypothesis. You should not, do not ever use the phrase that you're going to accept, and I'm going to write it here and then I'm going to erase it. You should never say you're going to accept the null hypothesis. That literally crawls Miss Ralston's skin and is statistically incorrect. Do not say it that way. I will count it wrong every time, all the time, because it is incorrect to say it that way. That is inappropriate. You have to say fail to reject. This is a big no, 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 no. Again, the idea here, if you think about it, I mean, it makes sense to me. Maybe it wouldn't make sense to you, but failing to reject the null hypothesis is like saying the person is not guilty and our null hypothesis is true, correct, or valid. Okay, and notice, even in a court case, notice how we word it. We say they're not guilty. We do not come back and say that the defendant is innocent. We just say they're not guilty. Based on the evidence, there is not enough evidence to convince the jury that he did the crime of which he is accused. Okay? We come back and say he's not guilty, meaning there's not enough evidence to convince me that he did it. He really could have done it, but there's not enough evidence. So we never come back in a jury trial and say a person is innocent. That would be like saying accept the null hypothesis, which is a big no-no. Okay, so be sure you use the correct phrasing. You reject the null or you fail to reject the null. And you make that decision on what you're going to do by comparing the p-value, which will be calculated for you by Minitab, and the level of significance that's going to be given to you in the problem. And here's what the rule says. The guidelines say, and these guidelines do not change, they're the same today, tomorrow, forever, and ever, and ever, and ever. If the p-value is less than or equal to the level of significance, then you reject the null hypothesis. In symbols, we write p is less than or equal to alpha. We reject the null. If your p-value is less than or equal to the level of significance, you reject the null every time, all the time. If the p-value is greater than the level of significance, then you fail to reject the null hypothesis. So if p is greater than alpha, you fail to reject the null. Every time, all the time. The last step then, after you've made that decision about whether you're going to reject or fail to reject, you got to report it back out. Just like the jury has to come back out and tell the judge what they've decided. So you have to write a final conclusion in a complete sentence form. Complete, detailed sentence form. And that conclusion is written in terms of, I'm going to tell you in terms of the true hypothesis. It's actually in terms of the null hypothesis, and you have to include the level of significance. And I have kind of another fill in the blank form for how to word that conclusion so that hopefully you won't mess it up when we get there. But your conclusion should always be written in a complete, detailed sentence form, being sure to include the level of significance and address the quote true hypothesis. Okay, so that's the process. And I hope we have time to go through it tonight in relationship to normality when we get there. But do you have questions about this process, even though we haven't done it yet, before we move on? Okay, the next topic in this section in Module 3 has to do with parametric and non-parametric test. In Stat 1401, our focus is only on parametric test. You can take an entire course on parametric test. You can probably take an entire course on non-parametric test. We're going to look at a sampling of both. And so I want us to talk about what are the differences of a parametric versus a non-parametric. And then also, when do you know which one to use? So if we compare the two, you have parametric and non-parametric. I hope that you realize that the prefix non means not. So these are not parametric. So let's focus on parametric for a minute. Parametric tests are used only with quantitative data, typically data that's at either the interval or the ratio level. Okay, so parametric tests use only quantitative data. Parametric tests also make several assumptions about the distribution you're dealing with. And typically for a parametric test, the biggest assumption that we make is that we are dealing with a normal distribution, or we have a large enough sample such that we can apply the central limit theorem, which then forces our unknown distribution to be normal. Parametric test also assumes that the data set does not have any outliers. And it also assumes that if you're looking at more than one sample, that those multiple samples have the same or at least equivalent variances. They're approximately equal. Okay, so you have to assume if you have more than one sample that you have equal variances. So those are some pretty big assumptions, but usually we can justify those assumptions because we're going to be dealing with a large sample. One of the other key things about a parametric test is a parametric test tests or analyzes group means, the population mean, the population proportion mean. Okay, so the parametric test look at the means. Remember, the mean is a measure of center. Again, typically with a parametric test, you're going to have a large sample. The other thing about a parametric test is it says that a parametric test has more statistical power. Quote, power. The idea of statistical power is that the test is more likely to detect significant differences when they truly exist. Basically, in a sense, they're more accurate. They're more on target than non-parametric. So parametric tests are more powerful, and so they are the ones that we tend to use more often than not. And again, we're dealing with quantitative data. And so we deal with that on a more regular basis than we do qualitative. And so again, we tend to focus our analyses using parametric. But that doesn't mean that the non-parametric are not useful. Again, in some cases, they may actually be better. So in contrast, a non-parametric test, it can still be used with quantitative data, even if it's at the interval or ratio level. It can also be used with data that is ranked, something where you have some sense of order to it, or you can use it with qualitative data. So non-parametric, again, is the area where we are able to deal with qualitative data, which are words and phrases. One of the big pluses of a non-parametric test is it does not require a normal distribution. And often the distribution for a non-parametric test is not normal. In fact, we don't even have to know what type distribution we have to use a non-parametric test. They're often sometimes called a distribution-free test because I don't even have to know what type distribution I have in order to run a non-parametric test. You can have outliers within the non-parametric test. So if your sample has some outliers, it might be your analysis would be better using a non-parametric as opposed to a parametric. Also, we don't have to assume equal variances. They can be unequal. It can also be that we don't even know what they are. I don't have to know what they are either in order to use a non-parametric test. And so there are some researchers, quite honestly, that would argue for using non-parametric all the time. Again, I don't necessarily agree with that because that wasn't the way that I learned it, but there are some people that would argue that. Non-parametric is also good for small samples, but the other key difference between parametric and non-parametric is that non-parametric looks at the medians. Now remember, median is another measure of center, but it's not really a calculation. It is simply the value that's in the middle of the data set. And so that's why if I have a large number of outliers, it might be that my data is better represented by that median than it is by the mean. Because remember, outliers can cause your mean or your average to be inflated or deflated, depending on which end of the spectrum they're on. Non-parametric does allow for a small sample size, but the downside is it does have less statistical power. It's not as accurate as if you will, than a parametric test. There is pretty much for every parametric test, there is an equivalent non-parametric test, and we're going to be talking about some of those in this course. But the other decision you have to make is, when should I really use parametric? When should I use non-parametric? Again, quite honestly, in my thought, if I have quantitative data, I'm going to do parametric. But if I have qualitative data or ranked data, then I might want to consider a parametric test. So again, to think about it, if I have quantitative data, especially at interval or ratio level, I'm going to do parametric. I want to kind of be sure that my mean accurately represents the center of the distribution, which probably means I don't have any outliers that are affecting it. I don't have any outliers that are causing it to be too high or too low. and then again that I have a large sample, or I know that the distribution is approximately normal. Remember, if I know it's approximately normal, I can use the normal distribution or the z-test. If I have a large enough sample, I can apply the central limit theorem, which forces any unknown distribution to become normal. So again, that assumption that I have a normal distribution can be a valid one if I have a large enough sample. For non-parametric, and I've got a typo here. Oh, it hung up on me at the same place earlier today. Hold on, I have to go out and fix my PowerPoint because it's wanting to be finicky here. Okay, so for non-parametric, you can have quantitative data and then qualitative, and the qualitative data would be nominal or ordinal. I got it up underneath the wrong bullet there, but qualitative data that's either at the nominal or the ordinal level, meaning it could be ranked. Perhaps with non-parametric, you're looking at the median again as opposed to the mean, and so the median becomes a better representation of the center of the distribution. And again, that's typically true if you have a lot of outliers present, because again, the median is simply the value that's in the middle position. It's not really a calculation. And I can use non-parametric when I have a small sample, or I have some kind of unknown or non-normal distribution. And that's not to say you can't use a non-parametric if the distribution is normal. You can, but again, most oftentimes we're going to use parametric simply because it has more statistical power. And as I mentioned, for each parametric test, there is an equivalent non-parametric. And I've kind of given you a comparison here of the ones that we're going to be talking about in the course. We'll talk about the parametric test and then also talk about the non-parametric and look at how the two are similar as well as how they are different. And that is going to be throughout Module 3 and Module 4. Okay, so that's throughout Module 3 and Module 4. And then we're also going to consider what they call post hoc tests. Post hoc tests are some tests that you maybe do after the initial analysis. You kind of go that one step further or maybe two steps further in your analysis, specifically after you have conducted a parametric test. And the two that we're going to look at are called Cohen's D and Tukey's test or Tukey's test. So one of the first decisions that we have to make really when we're looking at are we going to do a parametric test or a non-parametric test is, do we have a normal distribution? So that leads us to the next topic, because the next topic has to do with what are called normality tests. Okay, so normality test let us determine whether the sample data has been drawn or taken from a normally distributed population within a given tolerance. So, you're going to have a little bit of margin of error here, but the normality test allows us to determine whether the sample data has been drawn from a normally distributed population. There are lots of different statistical tests that we can use if we have normal data or parametric data. We've learned about the one mean z-test in Stat 1401. We learned about the one mean t-test in Stat 1401. We learned about the one-way ANOVA. In this course, we're going to also talk about the two mean t-test, and I think we maybe talk about two-way ANOVA. I don't remember, but those are some statistical tests that where we have to assume we have normal data. And so it's important that we know whether that assumption is valid or is a good one or not, kind of before we start the test. Because if it's not, then I may want to consider using a non-parametric test. There are several different types of normality tests that exist. We are only going to discuss one of them, and it's called the Anderson-Darling test. Okay, it's called the Anderson-Darling test, and Minitab is going to present it both in is going to give it to you in a graphical form with the appropriate test statistics. Okay, so Minitab is going to do the calculations for us. All right, so the Anderson-Darling test is, again, a statistical test of whether or not a data set comes from a certain probability distribution. Anderson-Darling could be used to determine whether my sample comes from a uniform distribution or an exponential distribution or a binomial distribution. We're going to focus on whether it comes from a normal distribution, which is the most common use for the Anderson-Darling test. But now it could do any distribution. But again, our focus is on, does the sample come from a normal bell-shaped symmetrical distribution? So I want to talk about how to state your hypothesis and how to state your conclusion for the Anderson-Darling test. Okay, so again, you're going to have two opposing hypotheses. Okay, and remember that your null hypothesis has to imply equal, and your alternative has to imply not equal or less than, greater than. In this case, the null hypothesis will be stated in this way every time, all the time. Because the question is our distribution normal? So the null hypothesis will be, let's even make us a little note here. Okay, if you want to get down to the nitty-gritty here, our research question in this scenario would be, is the sample data taken from a normally distributed population? Now I put it kind of fancy dancy. Okay, it basically boils down to, did the sample come from a normal distribution? And ultimately your answer either has to be yes it did or no it didn't. And so our proposed answers, again written more formally, the null hypothesis would be, I got to get my mouse back up there, would be like saying yes. And so we say the sample data or the data follow or equal a normal distribution. The alternative would be like saying no, and we say the data does not follow, which would imply not equal a normal distribution. So I'm not breaking the rules. My null implies equal, means yes, it is a normal distribution, and the alternative is no or does not equal a normal distribution. Okay, guys, don't get fancy dancy. Write it exactly the way Miss Ralston has said. The conclusion then is we say preliminary analysis, because we were probably going to go a little bit further. Preliminary analysis showed the data set for the whatever the variable is, and you have to choose is or is not normally distributed, as assessed by AD, which stands for Anderson-Darling, and with a p-value equal to this. We normally, the AD stands for Anderson-Darling, because that's the test we're conducting. And you have the P, and the P is, we just shortcut p-value. We don't usually write p-value. We just say P equals. Okay, so that's what the P stands for. I have on the next slide the Minitab steps. Okay. And then we have an example. And so I'm going to copy this example over to my scratch paper as soon as I can get to my scratch paper. Now, it says, the Institutional Effectiveness and Strategic Initiatives Department at Georgia Highlands College wants to know if the ages of students in fall semester 2022 are normally distributed. A sample of all students in 2 different Stat 1401 classes at GHC are surveyed and the results are provided. Well, the results were not provided on that slide. That's because they're in a spreadsheet. And Miss Ralston posted the spreadsheet in D2L. It says example 1, Stat 1401 class survey. Okay, so I'm going to click on that data set and I'm going to save it to my desktop. And I notice that this is in the form .csv. So in order to get it into Minitab, I'm going to have to copy and paste. Okay, so let me get Minitab open first. Okay, so I have Minitab opened. I've downloaded the spreadsheet that was provided in D2L. We go to the corner and we copy the entire spreadsheet. You guys should have been doing this for a while. And we paste. Okay, so we're looking at, we want to know, are the ages for these 46 students, and I happen to know it's 46 because I'm the one that did the survey, 46 students is normally distributed, or did it come from a normal distribution? Okay, so again, if you want, you know, real formal, real detailed information here, okay, and you may not, but the question here would be, and it really gives it to you in the problem. The question is the, I should say are, because it's plural. Sorry, get my grammar correct. Are the ages of GHC students in fall semester 2022 normally distributed? Maybe I want to do some further analysis, and so I need to know if the ages are normally distributed. Now, it really says that in the question, guys. You don't have to, and that's not part of the process. You don't have to write out this question, but I'm trying to help you see that that's the question I'm trying to answer. But it says it wants to know if the ages in fall semester are normally distributed. So I just wrote it in question form. Again, you don't really have to do that. The first piece that you have to do is you have to write state the two hypotheses. That was step one in the hypothesis testing process. So the first step is you're going to propose your answer to this question, and you label them. You have to label them H sub O for the null and H sub A for the alternative. And guys, typically when you write these, the null hypothesis goes on the top and the alternative goes on the bottom. They're stacked on top of each other. The null goes on the top and the alternative goes on the bottom. And so then we're going to say the data follow a normal distribution. That's the exact sentence with one word missing. I didn't put sample in there, but that's okay. The data follow a normal distribution. The alternative is the data do not follow a normal distribution. Now, in this case, in terms of identifying the information, in this case, the information that you need is this raw data. Okay, you can't do a test for normality without the raw data. Okay, so if you want to make a note about that, okay, so for step two in the hypothesis testing process, where you have to identify the players, if you will, your players, the information that you need is the raw data. For your sample, okay, which is provided. Then step three, you decide which test. Well, my question is related to normality. I'm only going to learn about one test for normality, so I know that I need to conduct the Anderson-Darling test for normality. Okay, that's the only one I'm learning about in relationship to a normal distribution. So it's my only option. Then step 4 is where we got to do our Minitab stuff. Okay, because we ultimately need our test statistic, which is the Anderson-Darling, and we need our p-value. So I'm going out to Minitab now to do those calculations. Okay, they're on the slides, but here you go. Stat, basic statistics. You're going to scroll way down to the bottom. It says Normality Test. I have to choose the variable. I'm interested in age. Percentile lines, we mark none. That's the default. Test for normality, we want the Anderson-Darling. And then we click OK. And it comes up in graph form. Okay, so I'm going to copy this. over to my paper so we can talk about it. Okay, so you get what is called the probability plot. Now, for it to be normal, basically what should happen visually is these dots should kind of be on this red line. Okay, on this red line. Well, you can really see that they're not. Okay, but then off to the side, you have several pieces of information. You have the mean of the sample, you have the standard deviation of the sample, you have the sample size, and then you have the two pieces of information that you need. You have AD, which is the Anderson-Darling, and you have the p-value. Now, this p-value looks a little odd maybe because it says less than 0.005. Okay, for our purposes, we're going to ignore the less than. That just means it's a really, really small number, and Minitab didn't bother to calculate it. Just ignore the less than. Okay, but your information is right there, so I'm going to write it down. So from that printout, I know that my Anderson-Darling is 7.020, and my p-value is 0.005. Yes, I realize that Minitab says less than. I'm going to ignore it and use 0.005. All right, then step 5 is where we make a decision. And we make our decision by comparing the p-value to the level of significance, which I think Ms. Ralston forgot to give you in the problem. Let's see. Yes, I did. I forgot to give you a level of significance. So let's just say use a 0.05 level of significance. Okay. Typically, if there's not one given, that's the rule of thumb because that's the most commonly used one. Okay. It really doesn't matter. But again, that would be the one if I wasn't given the value that I would most likely use. Okay, so my level of significance, which Ms. Ralston just gave me, is 0.05. My p-value from Minitab was 0.005, and we need to compare those two decimals. Now, guys, in my 29 years of experience, for whatever reason, students struggle to compare these two decimals. The easiest way to do it is to do it digit for digit. Okay, so if I look at the first digit after the decimal in both numbers, they're the same. If I look at the second digit, they're not the same, and I can compare them just like regular old numbers. So 0 compared to 5. 0 is less than 5, so the p-value is less than or equal to the level of significance. The guideline said if the p-value is less than or equal to the level of significance, then we reject the null hypothesis. Guys, you have to write this statement. You need to show me the numbers, show me the comparison between the p-value and the level of significance, and then you have to state your decision, whether to reject or fail to reject the null hypothesis. And then step 6 here is to write a conclusion. Now, let's backtrack for just a minute. We have made the decision that we are going to reject the null. Okay, so let me go back up here to where I stated my null and my alternative. We are rejecting the null. If you reject the null, that means this statement is false or wrong. And so by default, then, that means the alternative is true or correct in this case. So in this case, what we have proven or verified is that the data do not follow a normal distribution, because you got to follow the logic. So when I write my conclusion, we're going to use the same wording that was on this slide. Preliminary analysis showed the data set. Okay, so we're going to say preliminary analysis of the data set for ages of GHC students in fall 2022 is not normally distributed as assessed by Anderson-Darling equals 7.020 with a p-value of 0.005. Guys, I wrote this sentence. I added in the variable. When you add in the variable, put in the details. Who, where, what, when. And then I had to state, I had to choose between is and is not. And we had determined it was not. So we used the phrase is not. Questions? Okay, the second example says, get to it. A local bank manager wants to know if the ages of loan applicants is normally distributed, and a sample of 30 loan applicants is provided. And again, I forgot to give you the level of significance. So let's use 0.05 level of significance. Again, if it's not given, that's generally the rule of thumb. Okay. Again, the data was not given there with the question, but it is in D2L. Example 2, loan applicants. Now this one is actually a MTW file. It's a Minitab file, so I'm going to save it. But remember, I'm not going to try to open it because it'll give me an error. Because it's a Minitab one, I'm going to go out to Minitab. I'm going to tell Minitab I need a new worksheet. And then I'm going to open the worksheet that I just pulled down, put it on my desktop, was loan application or loan applicants. And so I get loan applicants. Okay. So let's walk through this question again. Again, if you want to be real formal about it, And again, this is really not part of the question, but if you wanted to be formal, the question is, are the ages of loan applicants, and it doesn't always have to be ages, guys, it just happens the two examples that I pulled, are the ages of loan applicants normally distributed? And so again, ultimately, we begin by posing an answer to that question. So step one in the process is to state the hypotheses. Excuse me. Okay, so again, you would have your null hypothesis on the top and the alternative on the bottom. We stack them. Oh, don't do that. Okay, and so the null hypothesis would be the data follow a normal distribution. Again, that's like saying, yes, it is normally distributed. H sub A, the alternative would be the data do not follow a normal distribution. Okay, so there's your hypotheses. Again, for this test, the second step in the hypothesis testing process is to identify the players. But when we are looking at this idea of normality, we do have to have the raw data. So we need the raw data for the ages of loan applicants. Which we have because Ms. Ralston provided it in D2L. Then step 3 is which test. Again, this question itself is about whether or not we have a normal distribution. And so the only test that we're talking about in relationship to a normal distribution or normality is the Anderson-Darling. So we're going to conduct the Anderson-Darling test of normality again. Now, again, you don't have to write the steps out as I'm doing it here, okay? Some of it you can go through in your head, but I'm trying to be deliberate for your benefit so that when you go back and look at this, you'll know what we were talking about. Step 4 is where we go out to Minitab to calculate our test statistic, which is the Anderson-Darling, and the corresponding p-value. So I'm going back out to Minitab. I have my data set on loan applicants. So we go Stat, Basic Statistics, scroll to the bottom to Normality Test. My variable this time is age. No percentile lines. We're doing Anderson-Darling, and I click OK. And again, it comes up and gives me the probability plot. And again, this one you can see, if you look at it in comparison to the previous example, you can see that the dots a little bit more kind of wrapped around that red line. Again, you're given the mean, the standard deviation, the sample size, and then you have your Anderson-Darling and its corresponding p-value. Okay, so I'm going to write those down. My Anderson-Darling is 0.659. The corresponding p-value is 0.077, if I looked at it right. And I did. Okay, so then I've got that recorded, and so I'm going to go and do step 5. Step 5 is we make a decision. To make a decision, we compare the p-value to the level of significance, which I gave you earlier as 0.05. Okay, my p-value from Minitab was 0.077. Again, the best way to do this, guys, is to compare it digit for digit. So the first digit after the decimal, 0 compared to 0, they're the same. Second digit, I have 7 for the p-value and 5 for the level of significance. So 7 compared to 5, 7 is greater than 5. So the p-value is greater than the level of significance. The guideline says if the p-value is greater than the level of significance, we fail to reject the null. Now again, to think about what that means. We have said we fail to reject the null. So if we fail to reject null, that means that the null hypothesis is true or correct in this scenario, in that we do have a normal distribution. And that would then by default mean that the alternative is false or wrong. And it's important to know which one of those is the case so that you can write your final conclusion, which is step 6. Okay, so our conclusion would read preliminary analysis of, make sure I say it right, I don't want to get it wrong, of, or show the data set, sorry. Preliminary analysis showed the data set of ages of loan applicants is normally distributed as assessed by Anderson-Darling, and I got to get that number, 0.659, with a p-value 0.077. Okay, questions? Okay, so let me remind you then that you must take the required proctored midterm by Saturday, which is October the 8th at 11:30 p.m. Please do not wait until the last minute. You have to have 2 full hours. You cannot stop, start, stop, start. Again, it's not going to cut you off at 2 hours. It'll just notify me that you worked longer than 2 hours. There are some formulas that are strongly recommended that you put on your note sheet for the final. Those are on the study guide for the week 7 announcement. Again, there is a review sheet with an answer key, and I will correct that attachment as soon as we're finished. And also remember that mini project 2, which is related to confidence intervals, is due by Monday, October the 10th at 11:30 p.m. Do you have any questions? Okay, if not, we're going to finish a little bit early tonight. You have plenty to do. So we will end there and pick up our discussion of Module 3 next Tuesday. Y'all have a good evening.